All right, welcome to the Explainer. Today, we're diving straight under the hood to look at the absolute engine of machine intelligence. We're completely leaving abstract textbook math behind us. Instead, we're going to learn how to actively command, steer, and drive these incredibly complex neural architectures. Just imagine for a second, standing at a massive control board. It's completely shrouded in this thick, million-dimensional fog, and you're tasked with perfectly tuning 1 million individual sliders just to safely land a plane. Honestly, that's the daunting reality of training a neural network. You simply cannot sit there and tune them one at a time. It's impossible. Manually calculating a partial derivative? It's literally like slowly, painstakingly moving just one of those sliders to see what happens. But the gradient? Well, the gradient is a totally different beast. It moves that entire bank of 1 million sliders simultaneously. It's this powerful, perfectly coordinated wave of adjustment.
Section 1. The unifying vector.
So the crucial concept to wrap our heads around is this: unify, steer, navigate, and optimize. The gradient is your ultimate steering wheel. It takes all this fragmented, localized data and unifies it into one singular, purposeful direction. It's absolutely the core mechanism that allows us to command these massive neural networks.
Believe it or not, this concept actually originated way back with 19th century physicists who were trying to track heat flow in 3D space. They realized pretty quickly that heat doesn't just flow neatly along an X or Y axis, right? It flows along the path of steepest descent. And this realization led mathematicians to formalize this unifying vector operator. They even named it the nabla, after the shape of an ancient Hebrew harp. Fast forward to today, and we've taken that exact same mathematical harp and we're using it to steer artificial intelligence. Crazy, right?
Section 2. Navigating steepest descent.
Okay, imagine you're blindfolded on a massive mountain, and your only goal is to get to the very bottom as fast as humanly possible. The catch? You can only feel the slope directly under your feet. A contour map is basically a topographic representation, where lines connect points of equal elevation, or in our world, equal loss or error. If you were to walk exactly along one of these lines, your error wouldn't change at all.
Now, this is an active, highly dynamic process. Every single time our model takes a step, the gradient recalculates. Picture this: a gold vector that actively rotates to point exactly perpendicular, or orthogonal, to the contour line. It is constantly seeking out the steepest ascent, instantly recalculating with every single move the machine makes.
But remember, we're trying to get to the bottom of the mountain, right? Because we want to minimize our error, we just drive the machine in the exact opposite direction, the negative gradient. We just follow that inverted vector straight down into the valley of low loss.
To really get this, conceptualize it as a literal vehicle. The vector's direction, that's your steering wheel, guiding the way. And its magnitude, which is calculated by the square root of its squared components, acts as your speedometer. It tells you exactly how steep the terrain is. High magnitude means you're teetering on a cliff edge. Zero magnitude, well, you've hit flat ground.
Section 3. When math becomes code.
So in machine learning, parameters are grouped into massive tensors. Say you have a weight matrix of 256 by 512. That is over 131,000 parameters. Because the gradient has to provide a direction for every single one of those weights simultaneously, its tensor has to match that exact shape. This effectively doubles the VRAM, the video RAM, required to run your model on a GPU. We're talking about a massive computational payload here.
And right here, this is the exact moment where theoretical math becomes executable code. In PyTorch, this entire massively complex operation comes down to one singular, beautiful command: loss.backward.
Calling this one elegant method triggers PyTorch's autograd engine. Under the hood, this engine seamlessly traverses the entire computational graph in reverse. It calculates every local partial derivative, and then it accumulates them into that unified exact shape tensor we just talked about. Honestly, it's an absolute marvel of software engineering, just doing all the heavy lifting of calculus completely behind the scenes.
Section 4. Steering machine intelligence.
But piloting a machine this powerful requires some strict safety protocols. For example, if you forget to zero your gradients between steps using optimizer.zero_grads, PyTorch will just continuously sum them up. Your model might look like it's training perfectly for a second, and then bam, it violently diverges off a mathematical cliff because the gradients just grew without bound. You also have to carefully manage your foundational parameters, which we call leaf tensors, just to avoid completely collapsing your system.
To prevent these kinds of catastrophic updates, engineers used literal safety belts. Take gradient clipping, for instance. In complex models, gradient magnitudes can spike massively. Clipping steps in and scales down those massive spikes, perfectly preserving your steering direction while hard capping the speedometer so you don't crash. We also use gradient accumulation to simulate larger batch sizes and mix precision to double our speed while safely managing all that memory.
Which brings us to the optimizer's role. Raw gradients are incredibly powerful, for sure. But modern optimizers like Atom take this raw gradient and scale it by its historical variance. Think of it like adding heavy-duty shock absorbers to our vehicle. Instead of just blindly following the steepest local drop and potentially bouncing off the walls of some deep ravine, Atom smooths out the journey, letting us efficiently navigate these crazy high-dimensional landscapes.
And that brings us to the ultimate frontier. Because the gradient only evaluates the slope directly under its feet, it simply can't see over the horizon of a complex landscape. It's essentially nearsighted. So we're left with this massive open question at the absolute cutting edge of AI research. How do we teach these machines to escape deceptive local valleys when their ultimate steering wheel can't see the bigger picture? It's a fascinating challenge, and honestly, it's exactly what the next generation of engineers is going to have to solve.